Okay, and with that, great pleasure to introduce our main keynote of the day, Andrea Stocco. He is an associate professor at University of Washington in the psychology department, and I think this is going to bring a very nice, interesting cognitive, psychological perspective to the day.
Thank you. Thank you for having me. I wanted to, originally I thought I was going to start this talk by saying, hey, now for something completely different, I'm a neuroscientist. But then I discovered that the metacognitive community is made of secret cognitive and neuroscientists. So I feel I'm back to being with colleagues, and I'm very pleased by this. So I've been kind of involved a little bit in problems with metacognition for a while, but I'm going to tell you, before getting into what I want to show you, I'm going to tell you how this started. About a couple of years ago, there was this interesting effect that became famous. Many of you might have heard about it. In biology journals, people start citing all of a sudden this technique, vegetative electron microscopy. Now, if you know anything about biology and microscopy, you know this is like an absolute nonsense. What is this thing? Well, in 2024, people were able to trace it to the fact that this paper was incorrectly parsed and added to large language models in the training data set. And of course, large language models don't have a great sense of what this means, but they regurgitate these words very well. And it was really strange because this is something that if you have any knowledge about what these papers are about, you should know this is a nonsensical technique. It cannot exist. There is nothing that makes sense out of it. But of course, they don't. And this is part of a general phenomenon we're all very well aware of. Colleagues at my university, like Emily Bender and Carl Bergstrom, have been pointing out that these machines seem to be hallucinating like constantly, and it's really hard to fix. This is actually something that Carl actually put in his recent recent book, like The Bullshit Machine, where he gave examples of Gemini answers to questions that are completely nonsensical. In case you don't know, the University of Washington was founded 150 years ago. None of these presidents were even alive at that time. And this was surprising because on the face, things like ChatGPT are actually pretty good at passing what we could consider metacognitive tests. This is an example of a false belief question. This is the kind of stuff that children do not pass until they are 4 or 5. And if you do this kind of experiment or version of the experiment, not with words but with situations, not even apes can pass this test. But ChatGPT aces it. It knows exactly like how to take perspective in different points of view, how to take the perspective of different agents, and even tells you, hey, this is a false belief test. So if you were to rate these metacognitive skills, it will pass. But the story is not so simple. While I was thinking about these things, my former student, Bridget Leonard, was also working on large language models, but from a different perspective, the perspective of like essential perspective taking in analyzing a picture. And she found out something really interesting. If you ask well, she analyzed a bunch of different multimodal transformer models, but all of them tend to have this interesting characteristic. If you ask them to analyze a particular picture where there is an agent, a human agent, facing in one particular direction, and then you ask them what is to the right of this person, from that person's point of view, or what is in front of this person, from that person's point of view, they tend to make systematic mistakes. Now I'm going to ask you to ignore the green curve. I'm going to come back to it in about 15 minutes. I'm going to ask you just to look at the blue and red curves, which are the accuracy performance. And as we rotate the position of the person, the systems tend to give a stereotypical response. What is to the left or right or in front of, based on what you see, but not based on the perspective of the person. This was really surprising, and it made me and my colleagues think a lot about what does it mean also for metacognition with respect to humans. And this is the realm where we actually live, because we're neuroscientists by training. So I'm going to ask a question to you, because this is the first thing that we notice. What would you say is the good definition of metacognition? Anyone? Anyone? I've seen a lot of slides, and I updated the next slide while I was taking notes. Yes, Bonnie?
Thinking about one's own thinking.
Thinking about one's own thinking. Very good one. Any other? Yes, Peter?
The statue you had at the beginning, sitting in the toilet.
Oh, okay, yes, that's great. Yes, the thinker. And the other, yes.
The problem is to define what you mean by thinking, okay?
Oh,
And
we're getting close.
Everybody understands it differently, and what we're processing metaphors.
Very, very good. You're actually stealing the thunder to the rest of my slides. I ask these questions a lot, and I took some definitions here. So it turns out that we often do not talk about the same thing, even within this community. For instance, reflecting on one's knowledge is very common, and is the standard question that also my colleagues will give. Reflecting on one mental processing is also really good. Like, this is not about the knowledge, like things like, I don't know what the answer to this question is, but it's like, wait, how did I come up with this answer? Another variation is the false belief task, the type of thing that educational psychologists care about. Reflecting on another person's mental processes. This is the type of thing where we're trying to, for instance, do adversarial simulations, try to understand what another agent is doing and what they are doing. And it turns out that you can go to the list of the literature and you're going to see like dozens of different definitions, and they all have the same name, metacognition. But this is a problem because we're not talking about the same phenomenon. So we need to adopt some kind of like taxonomy, and I'm not going to push for one taxonomy in particular, but there is one that struck me that was introduced by Flavel, who was an educational psychologist. And he noticed that we talk sometimes about metacognitive knowledge, what we know, we don't know, for example, and sometimes we talk about the metacognitive experience, which is like the feeling of, wait, there's something wrong here, you're asking me a question, but I don't recognize this data. And for simplicity, in actually the paper that we co-wrote with Christian and Robert and we published in the book that Paul has edited, we call this the process deliberate metacognition versus automatic. And I'm going to give a very quick definition right now, also citing my favorite painter, Magritte. So deliberate metacognition is really like reasoning. All of these processes are not things that are special, even when you're talking like something like the false belief task. It requires just very careful analysis of what are the stimuli, what is that is being asked, and what are the actions that we need to take, the cognitive steps that we need to take to give an answer. In general, these are the things that where there is a problem is detected, the problem can be fixed by adding more knowledge. And in psychological parallel, this is what we would call a system 2 type of thing. Something that can be controlled, is not automatic, and is very easy for the agent to describe. But there are a bunch of other phenomena, and some of them were addressed here, and I was really happy when they came up, that I'm going to call automatic metacognition. Now, I couldn't find a Belgian painter, so I apologize. I actually improvised a sketch to give the idea. And these are moments that, for lack of a better word, we are exposed to the inner world of our brain, or the way our mind thinks. These are things that we somehow can sense, or like this feeling of unease when I have conflicting answers, the feeling of surprise, we're like, oh, I never thought about this, for instance, are all things where we have a kind of like a perception that there is something off, and this perception becomes conscious enough that we can think about it. Bonnie used a wonderful term about it, triggers for metacognitive reasoning. Now, to understand the distinction between the two, as you pointed out very correctly, you need to have an idea of what the reasoning system underlying is. Because I can put the boundary between deliberate and automatic in different parts of the spectrum, depending on what the underlying engine for reasoning is, what the underlying engine for thought is. Now, it turns out that I've been luckily involved in a bunch of work where John Leary, Christian Andrea, and Paul Rosenblum have systematized this with respect to cognitive architectures and usefully for us to both cognition and neuroscience. In 2017, they wrote this paper where they summarized a bunch of lessons that they learned from developing cognitive architectures in robotics, neuroscience, cognition, psychology, and they noticed that over the course of 40 years, these are different systems have kind of converged on a set of assumptions. And probably the set of assumptions are very useful to build very robust systems, but also are probably true in general of the human mind and brain. And I'm going to summarize very quickly what these assumptions are, and they are that The system cognition tends to be modular and it tends to be made of at least 5 components: long-term procedural memory, long-term declarative memory, global workspace or working memory, where symbolic information can be put, and then the classic perception and action systems. The idea of this common model of cognition, as it has been renamed, is that there is a set of symbolic data at the beginning, which is where the deliberate part lives, and a set of metadata, which is what gives priority to the PCO nodes that are extracted, for instance, is used to make the system work. Now, I became obsessed with this about 5 years ago, me and my graduate student, so we actually tried very hard to see whether this was true, this was an architecture that could work in the human brain. And please bear with me, because soon I'm going to take a very deep dive into the brain and why this is important. But first I want to show you that you can identify these 5 components with different functional regions in the brain. I color-coded them, and these identifications don't come from random, like, picking spots that seem right, but they come actually from a series of studies where we look at different studies from different groups of people doing different tasks, and where we analyze systematically brain activity to see which parts of the brain would better map with this component. Now, the way to do this, just to give you an idea, I didn't just pull it out of my imagination. The way to do this systematically was to consider this idea of the common model of cognition as a network system. Eventually, this is something that is telling us how these pieces are connected, and if it's a network system, you can imagine the different stimuli that I'm presenting in an experiment are just things that activate this node, and then this information flows through the system. When you do this, you can get predictions for what brain activity looks like in these different regions, and you can compare the predictions of the model against other models, for instance. So we did this extensively across all different tasks and comparing a bunch of different architectures, but it turns out, as you can see from these red distributions here, the common model of cognition as an architecture of the brain just dramatically outperforms any other thing that you can have as a model, as a higher level architecture of the brain. There is no way you can wire the system in a better way. We did this, we are very pleased with it, but now I want to go back and show you something really interesting. So one of the tenets of the common model of cognition is that there is a division, something very neat, between symbolic metadata, which is where the boxes are and what the boxes contain, and the other things, like the metadata stays around these symbolic entities, and it's really important to make the system work. So this is what Christian Andrea calls the separation of church and state in the common model of cognition. So there is a symbolic part in the middle, and this is where the cognitive cycle, the cognitive action happens. And then there are other things that are laying around, but they are not available to the system itself. They are needed because the architecture needs to select, for instance, something that needs to be put in working memory, and this is a process that requires competition between different declarative representations, and they are typically ranked by activation. Or if you have to select a procedural rule or an action, you can select it based on rewards, Q values, and reinforcement learning. But it's not the system can tell you, oh, this is the Q value I made the selection with. And this is something that tends to be very true about our own cognition and our own brain. There is a line that is very hard sometimes to spot between what is available to us and what is instead not available to us in terms of computations. Now, this is my favorite example and my favorite demo. Please bear with me. So there is a normal part of our cognition that is devoted to things like walking, going to talks, drinking coffee, and being around. We are not super aware of it, but we can control it. Now, do this with me, please. Extend your arm and put the thumb back. Great. Now, one of the things that our brain does really easily is keep track of our head is in space. Now, I'm going to ask you to move your head back and forth at about 1 hertz, like that, and keep looking at the thumb. It's pretty easy, right? Now, stop your head. Now, do the same thing, but instead of moving the head, just move your arm left and right 1 hertz, and keep track of the thumb. Now, all of a sudden, this is really hard. Now, the reason why this is really hard is because there is a specific circuit that keeps stabilizing our head and gaze, and we're not aware of it. But the opposite, the inverse computation, which is exactly like just the matrix inversion of the other one, is really hard because we don't have a circuit for doing that. We learned how to do that because it's actually really convenient to keep track of objects in the world, but this is a deliberate strategy that we learned. It's not an automatic mechanism. And this is just one of the many examples that I can give you of things where I cannot put the boundary, but I know that one part of the computation is in the implicit side, and the other part is actually something that is part of the cognitive cycle. Following your thumb as you move your arm is here. It's something that you know how to do, you can control. Keeping your head stabilized to look in a direction is part of the architectural part of your brain. And of course, somewhere you can identify these two pieces with the two different aspects of metacognition and dimension. The deliberate metacognition is something that exists somewhere in the cognitive cycle, in the symbolic part of cognition. But the other part, which is interesting for us, the part that Bobby called the cognitive triggers, well, this is something that happens where these computations somehow become available. Now, I don't know, as I mentioned before, where this line lies, but I thought it would be easy to make a list of phenomena that we would all agree somehow belongs to these red arrows, things where all of a sudden the inner processes of the brain become available because they give rise to an impulse. And together with my colleagues, we came up with a list of 4 phenomena that we could all agree, okay, these are part of this automatic metacognition. The first one is feeling unknown, tip of the tongue, déjà vu. This is something that humans are really good. If you ever watch like quiz shows, one of the things that will surprise me is how fast people press the button when they know the answer. Most of the time, they press the button before they can retrieve the answer because as a memory neuroscientist, I know it takes you a long time to retrieve a piece of information, but people respond with the speed of an athlete. And in fact, there are classic experiments in psychology that show that when people are given the option to gain a lot of points by answering very fast that they know the answer, versus actually doing the explicit calculations, kind of a arithmetic task, people are incredibly accurate. Before even coming up with the correct answer, they know that they can get the answer. And this kind of thing suggests that there is a way in which you know about something that is in your memory before you actually can test for this knowledge. Of course, sometimes you're going to make mistakes, but people are really good at it. In terms of what Alex talked about, this is really good alpha competence that people have about their own memory. Another interesting phenomenon that came up over and over is decision confidence. To me, it's always really surprising that people are sure about something that they have decided. And incredibly enough, everybody agrees that even when there are really not much priors, not much explicit knowledge to go about, people have a good gut feeling about what they do. In fact, there is this famous experiment where people were given like very ambiguous shapes, but surprisingly, their confidence judgment after every trial was really highly correlated with their performance. People were good, even in conditions of extreme uncertainty, at gauging how good the performance was. Another thing that is fairly known or fairly common as a phenomenon is the sense of response conflict. As a cognitive psychologist, my favorite example is the Stroop task, which is like the bread and butter of every kind of graduate student in psychology. It's really easy to answer a question like, what is the color this word are printed in when the word and the color match? The first square that you see is blue. When the two don't match, it becomes complicated. It's really hard to say red because you really want to say green. And people are accurate. It's not that people make mistakes about this, but if you observe the response times, when they see green written in red, they slow down. And in fact, they slow down even the following trial. Because there is this internal sense of like, wait, I'm about to make a mistake here. This is really fast. These are actually effects that happen in the order of a few hundred milliseconds before, in a sense, our deliberate cognition kicks in, but enough to trigger some deliberate strategy like slow down, think twice, check your answer. And then one of my favorite examples is violation of expectations. This is something that is hard to define, but is ubiquitous. And sometimes it shows up in things like, oh, I don't have the resources to do this task. I need to think about it in a different way. This is my favorite experiment. this is an experiment in which the authors taught college undergraduates at Carnegie Mellon how to do kind of like arbitrary mathematical operators. In this case, they invented this thing called pyramid algebra. So 8 operator 4 is just kind of like a repeated sum of items where 8 is the start and 4 is the number of steps you have to take, and the clue is the number. And then I ask people to do simple tasks like what is 8 operator 3, what is 2 operator 4, and so on. And then at some point they throw an oddball problem like what is 200 operator 401? Now, before this problem, the time it takes for people to solve the problem is proportional to the number of steps. But when they see this problem, nobody starts doing 401 sums. Everybody stops, thinks a second, and then starts reasoning, some doing deliberate reasoning about the nature of this problem. They say the correct answer, which is 0. What is really interesting is that people know that will take a long time to compute, and that they shouldn't do it. And this is something that is another trigger. It causes a reflection into what you should be doing. Now, I want to point out one thing. These 4 phenomena, we decided they were all automatic metacognition, but they're studied in psychology in completely different domains. Nobody has called them metacognitive phenomena. People study them in different fields for different reasons. And typically when they study, it's because they are interested in parts of the brain that are very specific. Like, for instance, people who study confidence in decision making are really focused on these dopamine systems that give value to choices. People who study feeling of knowing are really memory psychologists, who are really interested in regions like the hippocampus. And so we thought, this is really exciting because maybe there is a commonality that has been missed in the field for a long time. So we decided to just look at what people have studied and do a meta-analysis. A lot of the studies have been done in the scanner. Many studies are confounded by other things, but we can select from the huge amount of literature all the studies that we think are relevant, pure examples of the metacognitive processes, and just pull them together and analyze them. This is the procedure. This is like when we use something called the Prisma workflow, which is a way to screen carefully the previous studies. And there is a way to reconstruct from a variety of studies performed on different conditions, what is the likelihood of different parts of the brain being involved in this phenomenon. So I'm going to share the results now, because I thought that the results were the most surprising part of this endeavor. But first, I don't want to assume that everybody is a neuroscientist, although I'm starting to get my doubts now. We always toss pictures of brains everywhere, but I know it's always a little strange to understand if you're not familiar with the way things are. So this is like what the brain looks like, and you're going to see a bunch of numbers, but typically we plot the brains with numbers associated to positions, and numbers that are negative on this type of drawings represent things that are on the left, positive represent things that are on the right, positive in this direction represent things that are up, negative represent things that are down. And this is what we found for the feeling of knowing. We selected 13 studies that are pure feeling of knowing fMRI studies, and they show up consistent activation and recruitment of these regions. Now something, to you probably this might not mean much, but to me, that already attracted my attention. And I want to focus on these 3 different regions. Because the regions that are not commonly showing up in fMRI studies. This is what attracted my attention. They are the left and right insula and something called the medial frontal cortex. I circle them because they're going to show up again. Because when we analyze fMRI studies involving decision confidence specifically, you see some similarities, some overlap, but you also see, again, the same 3 regions in the same exact location. And the same thing happens when you analyze response conflict. You have a lot more activation. This is also the richer representation of studies that we've seen. And you see again, left and right insula, medial frontal cortex. And again, expectation variation studies, medial frontal cortex, left and right insula. And just to convince you, you can also plot them all together. And you can see that, yes, they are not always the same phenomena, the paradigm are different, but there is this kind of overlap in these strategic reasons. And because we have the images, we can just do a matrix N operation and just select the exact overlap. And the overlap, of course, is precisely these three regions that I pointed out, the left right insula and the medial frontal cortex. Now this is interesting to me because these are regions that are known in the literature, but it's not that people have a good explanation for what these regions do. They have different names. In functional neuroimaging, they are often known as the ventral attention network, which is kind of like a strange name for something that we don't understand well, but you understand a little bit what it hints at. It's like attention for internal states. In the clinical literature, this is known as the salience network. This is the type that tends to be hyperactive in, for instance, individuals who suffer from PTSD. It tends to be something that directs attention to threatening stimuli. It does also a bunch of other things. These regions are involved in pain. People who have lesions in these regions have distorted sense of pain. They feel less pain. They are also involved in interoception. This is like one of the strangest studies that I ever noticed. But apparently some people are really good at feeling their own heartbeat. I did an experiment at home. My wife is absolutely correct. I have no idea what my heartbeat is at any point in time. I need to check my Fitbit for that. But Krich et al., Igor Krich at UCLA, found out that the ability to perceive your own heartbeat is correlated with how active this particular network of three regions is. And finally, this is also a set of regions that are involved in taking perspective, like automatically detecting where another person's body is or what is their position. Now this is quite interesting because there is no direct connection between pain and heartbeat and large language models, for instance. This is exactly what the test that Bridget Leonard, my former student, did and showed that actually even sophisticated models like ChatGPT-4 fail. Now, for once, I want you to look at the green line, because this is not an accuracy line, this is actually the response times that you get from individuals when they are doing this task. And you can notice something. When the rotation is very small, large language models are correct, and response times for humans are very fast. But when you get into a strange situation where it's not obvious what the person is looking at, large language models fail dramatically. Humans are good, but they are doing something different. All of a sudden, they pause before giving an answer. This is again another signature of metacognitive trigger. Something else is kicking in. It's probably an automatic process that is telling you, wait a second, this position in space doesn't match. And what we're probably doing is simulating our own position and trying to imagine what would happen. But this is not something that this is something that we do automatically, but kicks in certain situations that are difficult. And when the situations are difficult, you can see the same process doesn't kick in for transformer-based models. Even more interesting is when we look back at the literature about what happens when this network of regions is not working properly. And interesting enough, you can find a lot of evidence that this network of region is downregulated in psychosis, people have strange beliefs, hallucinations, people who suffer from like visual, acoustic hallucinations, schizophrenia, which of course is correlated with both of them. Interesting enough, schizophrenia, unlike psychosis or just tendency to have hallucinations, has a genetic and inheritable component, and even the relatives of schizophrenic patients tend to have downregulating parts of this network. And finally, it shows up in confabulations. These are typical individuals who have some kind of memory disorder, but they tend to make up stuff. It's not that they are aware that they are lying, they just make up stories because they cannot distinguish anymore like where this piece of information comes from. Now, interesting enough, these are all words that have been used to describe things like the hallucinations that large language models suffer from. One thing that you may ask, like, okay, you have this network, but you talk a lot about the common model of cognition and these beautiful regions that seem to map to the modules of the common model of cognition. How do these two things match? And actually they match wonderfully. This is again in the same type of brain space, a plot of the 5 modules of that I showed before of the common model of cognition, but I added in magenta the network of regions that we talk about, this putatively automatic metacognitive network. And you can see that it fits very nicely. It kind of fits like a glove in the empty space left by the other regions. At the same time, it's not fitting in a random position, because there's plenty of empty space. It fits in a very strategic position. And this is what made me really excited about this network. If you were to plot this network in this diagram, you will notice that these regions are systematically located between long-term memory regions and working memory, and procedural memory regions and working memory. They are kind of like intermediate stages of processing for where you need to retrieve information or retrieve actions to perform. And because of this, they are probably extremely well suited to provide meta information to working memory, to your deliberate cycle engines, the global workspace where information is available. So to conclude, one thing that I wanted to point out is that this is very specific to this particular architecture, which we believe is true of the brain. But this is not the only possible architecture to build an intelligent system. This happens to be true of a lot of cognitive architectures, which of course were historically developed taking an inspiration from cognitive psychology and the human mind. This is true probably about the brain, based at least on the research that we've done. But there are many other architectures. And it turns out that different architectures offer different points of contact for automatic metacognition. This is actually one of the reasons why I was asking Brian about confidence and how confidence would they have in these models. An architecture like CNN offers an obvious point of contact, in a sense, for metacognitive reflection. You have, categorical endings at the top level, and you can extract a measure like, okay, what is the distribution of this, what is the entropy of these responses, that offers a natural point of, for metacognitive reflection. Transformers, I would say, it's really hard to do this. Partly because the output is a token or a sequence of tokens, so it's not something that is naturally connected to an obvious action, a discrete action, a discrete piece of knowledge. Partly because it's a feed-forward network where it's really hard to point to a specific piece that is easy, where it is easy to extract metacognitive information. Maybe the multi-head attention provides some important metacognitive information, but if it is, it's fundamentally different from the metacognitive information that we have in the human brain. And this is where the architecture and the nature of thought, how we represent it, becomes really important. All right, these are my conclusions. There's the first part that is in humans, and I feel we have not published this work yet, but I feel confident enough to present it to you when saying that there's a specific network of regions that is involved in metacognitive phenomena, and it's also connected to this kind of like interoceptive phenomena, which points to the idea that automatic metacognition, triggers for metacognition, are really the perception of one's own processes, are the few places where the underlying architecture is exposed. There are some implications for AI in general. Jokingly, I said to my students, like, the main implication is like, you need to make these models feel the pain. If they have a way to experience interception, well, maybe we solve the alignment problem, but we also have a way to make them understand where they need to stop, pause, and trigger a metacognitive reflection. The other point I want to make is metacognition is probably, at least in the automatic form, deeply tied to the underlying architecture, to the structure of this system that generates intelligent behavior. And the different architectures, because of this, probably allow different room for metacognitive abilities, and probably need different systems for metacognitive abilities. So metacognition will look very different in a transformer base versus something based on a different architecture, like, I don't know, Hinton's capsule-based system or something like this. And that's it. I want to take just 1 second to thank all the colleagues that helped me and I've started the work here, because they have done incredible work in supporting me and my students in this process. If you have any questions, I'll be happy to answer them. All right. Yes?
Thank you for a very interesting presentation. I have many questions. I'll ask just a few. The first one is that the type of approach that you described, natural, is modeled based on correlation. And this is not enough. So, but even with that, the task that you need to do if you want to kind of progress into computational modeling and system building, you need to have some connections and interface between system 1 and system 2. Yeah, so that's a question. And the other one is not fair. Feldman Barrett, as you know, said that there is no such thing as a particular area of the brain that displays something. Everything is entirely subject to plasticity. So it's a totally different question.
These are excellent questions and deep. I'm gonna actually start with the second one. So there is always like a huge amount of problem when you say an area does this or an area does this, because of the problem of plasticity and because of the fact that the brain is essentially not stable throughout development, but also because it's not that a particular set of neurons does something that we can give a name for. It's typically something that is related to network computations. Because of this, I'm always hesitant to talk about modules, and because of this, even in this case, in the case of the common model of cognition, which I advertise a lot, you can see that what we consider a module in an architecture is actually a distributed set of regions. So I am a strong believer that eventually what we consider a function is just like a particular set of neurons that are correlated, and throughout this cascade of operations gives rise to something that we can give a label on.
Yeah, but where is the semantics of this?
Well, this is the...
You know, that's where the real question is.
Absolutely, but the semantics is something that is a reverse inference, right? We don't know that a region does something. We know it is involved in some behavior more than another type of behavior that we see.
Yeah, but the question is whether you subscribe to Illuminativist philosophy.
Oh, I do not subscribe to the philosophy that there is a part of region that I absolutely don't. Yeah. The interesting thing though, and this is the part where I believe that brain science is helpful, there is a sense in which brain topology can give you important clues. And in particular, the idea that a region is located in between certain pathways, I think is something that is a powerful indicator of what this region could be doing. I forgot your first question.
No, it doesn't matter.
Okay.
So yeah, I actually have a few questions, and I apologize in advance. I'm not trying to turn this into like a graduate epistemology seminar or anything, but you had mentioned knowledge earlier, and I was just curious, like, how are we defining this? Because if you had said like justify true belief, I don't want to be like, but the Gettier problem, you know, to bring that. But in terms of like, you're coming presumably from like a cognitive science, neuroscience perspective, and not like a symbolic philosophy of like, well, knowledge is actually like this apprehension, and we actually have a justification mechanism that is sound. But on my end, like, there is actually like the symbolic derivation by which we can say, well, this is actually something that we are able to symbolically construct an argument for, and although we might not have a proof system for this, we're still like at least putting forward an evidence-based chain of argumentation, and that is different than the sort of instinctive reaction. Like, there's a cognitive deliberation there. Is that what we were meaning by one's knowledge of knowledge? And then I guess the sort of second related question is, because you had brought up like the Magritte and like the recursive process, are we suggesting that knowledge that arrives out of metacognition is a fixed point of that process, or is just something that emerges as something that's relatively stable upon iteration of metacognition?
These are really, okay. These are fascinating questions. So my point was actually a little bit shorter. I was using the lexicon that I derived from cognitive psychology, where knowledge is just a static piece of representation you can have, and typically knowledge is opposed to process, which is the mechanism very involved. Now, how you identify that in neural systems is even crazy, but to answer your question, no, it's static, but it's not fixed. So, something that triggers metacognition, for instance, is something like a momentary feeling that, okay, this is off, but it could disappear within a second.
Okay. Yeah, it's just like
no monotonic.
Okay.
Yeah.
We'll have to hold off on questions because we're eating into lunchtime. So let's thank Andrea again.